Okay, so I don't know if the person that asked that question has joined, but let me just go ahead to explain this. So the person was asking, how would you respond to a question that asks you to explain the effect of increase in pressure on you, right? So I said the first thing that you have to do, okay, the first thing you have to do is to tell them what will happen. Increase in pressure or increase in temperature will lead to what? A decrease in yield. Then you then explain why it will lead to decrease in yield. So you're explaining what and why. What and why. That's what will earn you your what? Your full marks. Okay? You're explaining what and why. Okay, I hope I answered that question. Cool. So let's give like 30 seconds for someone else to join. Then we'll move on. So the next topic we want to look at now is metals, right? We want to go straight to metals, and there's a whole lot under metals, right? A whole lot. We'll look into properties of metals first, okay? And I need your maximum attention. This is as important as, okay, as it can get, okay? So we are going to be starting with the properties of what? Properties of metals. Properties of metals. Now, this seems like something simple that you guys are familiar, with, but let's run through. Now, under properties of metals, there are two ways to look at it, right? We have different types of metals in your periodic table. We have the group 1 metals, group 2 metals, group 3 metals, right? Then we have the transition metals. So usually we are going to group together group 1, group 2, group 3 metals together as some special kind of metals. Then we are going to look at transition metals as other special kind of metals. Okay. So oftentimes questions will ask you to identify general properties of metals, then properties of metals that are unique to transition metals, then properties of metals that are unique to group 1 or group 2 metals. So please, that's the perspective you are going to look at it, right? We have general properties of metals, okay? Maybe I'll just go straight to quickly pinpoint those general, properties, general properties of metals there. If you can mention, fine. Everybody, just mention. You can use the chat room. Properties of metals that you know. General properties of metal that you know. General properties of metals that you know. Yes, use the chat room, or you can unmute yourself and just mention general properties of metals. Yeah, use the chat room and read them out quickly. Let's get engaged. High melting point, high boiling point, good conductors of heat. Yes, ductile, fantastic, fantastic. Yes, let's keep it coming. Malleable, good, good, good conductors of heat. Yeah, okay, fantastic. Go sonorous, yes, sonorous. Yeah, one more. Go ahead, one more. Sonorous, yes. They are shining when freshly cut. Right. Now, all these properties that you have mentioned, they are called the general properties of metal. And the truth is, not all metals have these properties. That's why we are looking at those two classifications, right? So we'll look at group 1 metals. Okay, group 1 metals and what? Transition what? Transition metals. You need to clinically understand the difference between them. For example, we said metals are hard, right? They are hard. But the truth is group 1 metals are not hard, they are soft. So you can see that way. So out of the general properties that you have listed, let's look at properties that are unique to group 1. Then properties that are unique to transition metals. Then we'll now go to metallic bonding and use metallic bonding to explain these general properties, okay? For group 1 metals, we say group 1 metals are what? They are soft, okay? Rubidium, for example, can be cut with what? With razor or knife. Number 2, group 1 metals have low what? Melting point. They have low boiling point. That is compared to transition metals. You need to know that, please. Not compared to non-metals. When you compare any metal with a non-metal, then you can say they have high melting point, they have high boiling point. Do you get that? They are hard, and so on. But when you are comparing group 1 metals to transition metals, group 1 metals are softer. They are soft, right? They have low melting point. They have low what? Low boiling point. Is that taken? Good. Then transition metals, their unique properties. Their unique properties would then say they have high what? Yes, group 1 metals have low density. That's another difference. Please be writing these key things down. Okay, transition metals have what? They have high melting point. They have what? They have high boiling point, right? They have what? They have high density. Can you see? If you are asked to differentiate between transition metals and group 1 or group 2 metals, these are the differences, okay? They have high melting point, high boiling point. They have what? They have high density. So then this is in terms of chemical properties. So we can go ahead to tell us that transition metals, what other properties do you think transition metals have? We have 4 other unique properties for transition, metals. They form colored compounds, right? They form what? Colored what? Colored compounds, if you like. They form colored complex. Okay. Yes, transition metals, they have variable what? Variable oxidation state. Variable oxidation state. Yes, any other property for transition metals? They form more than one compound with the same what? With the same element. They form more than one compound with the same what? With the same element. Then number 4, the 4th chemical properties, they form what? They form complex ions. They form what? They form complex what? Complex ions. Right? This is just overview for you to be able to see the difference between them. Group 1 metals don't form colored compounds. They are white. Okay? They are oxides, hydroxides, they are white. But when it comes to transition metals, they form colored compound. Like copper sulfate is blue. Are you getting that? Copper oxide is black. Iron 3 oxide is brown. Okay, because it's what? They are transition what? Metals. They are compounds of transition metals. Now, let's go back to the general properties of metals. Then, in these general properties, what is our focus? Our focus is that we want to use metallic bonding to explain the properties. For example, thermal conductivity, electrical conductivity, malleability and ductility, the melting and what? Boiling point. So let's start from the simplest. Okay, so you need to cast your mind back to what? Cast your mind back to metallic what? Metallic bonding, right? Because it is metallic bonding that you will use to explain these properties. And what are those properties? Melting and boiling point, malleability and ductility, right? Then electrical conductivity and what? Thermal conductivity. Now let's look at metallic bond. I want somebody to in 1 minute, can you recall what you understand by metallic bonding? Use this diagram. Yes, please, quickly.
So metallic bond is like positive metal ions that are joined together by a sea of delocalized electrons.
Okay. Positive metal ions joined together by a sea of delocalized electrons. So before the positive metal ions are formed, what happened to the metal? That's where to start from. Yes, what happened to the metal? Anyone? Or was that Ife? You can continue to explain. What happened to metal before it forms a positive metal core?
It loses its electrons.
Electron, fantastic, fantastic. So you have a piece of metal like this. Let's say this is a cut, right? So I'm going to be using student to represent each of the metal atom. Let's say this is Ife, this is Farida, this is Steno, this is Hikma, like that, 4 of them. Then I gave each of them a tennis ball. Okay, so but I just have 4 of them like this, but let's assume that there are 100 in a classroom, right? Each of them would drop the tennis ball. That tennis ball is the electron, right? So a metal can lose its electrons because that is what makes a metal a metal. It has a property to lose electrons, to form positive ion. But if I ask the student, 100 students in a court, each of them with a tennis ball, and I asked them to throw the tennis ball on the floor, right? The tennis ball will bounce all around the court. But each student will know that he or she has a tennis ball, but you can't tell which of the tennis ball is yours because the tennis ball will bouncing around. That's the meaning of what? Delocalized. They are no longer fixed to a particular point. They are no longer localized. They are no longer local balls. They are now international, interatomic. So the electrons can move around in the court. So that is the meaning of what? Delocalized electron. So when we use the word seal, what does it mean? It means many electrons. And it also means what? Moving, because sea has to do with current, ocean current. So we have sea of delocalized electron. The electrons are moving around, but there are many. Okay? So when the atom has lost electron, so we usually don't want to use the word lost electron because the electron is not lost totally per se. It is still within the metal, courts, right? But so each of the metal atom will donate the electrons toward a sea of delocalized electron. And when that is done, let's say each of this metal is sodium. Sodium will donate one electron and it becomes what? Sodium plus, right? Everybody knows that. So that is what we call what? The positive metal core. Positive what? Positive metal what? Metal core. So then we now have sea of delocalized what? Electron, right? So the bond that exists between the positive metal core and the sea of delocalized electron is what we call the metallic what? Bond. And that bond is an electrostatic force that is so strong that holds the metal to what? Together. It's like a it's like a thread that binds the metal core to what? Together. So metals have high melting and boiling point. You can trace it back to what? To the positive, to the sea of delocalized electron, to the bond between them. So if you have to explain why do metals have high melting and boiling point, you will tell us, you will refer to what? The strength of the metallic wall, metallic bond, right? Because the metal is held together by what? By strong metallic wall, metallic bond, and therefore requires what? High temperature, high amount of heat energy to what? To break the bond. Hence, it has high melting and boiling point. It's like a bomber to bomber theory. Can you see the way I took it? I first refer to what? To the bond between them. You are going to name the bond. What is the bond? Strong metallic bond, right? Then I also refer to the strength of the bond. I said this bond is what? Is strong. Then what is the implication? Then you now talk about heat energy. It's going to require what? High amount of heat energy to break the bond. Then lastly, it's going to have high melting and boiling point. Can you see the way I connect everything? Don't jump the gun. If you jump the gun, you are going to be fired by zero. Okay? So now the next thing is malleability and conductivity, and ductility rather. Malleability. When you say malleable, it means that a piece of metal can be beaten into shape without losing its what? Its structure, without breaking. That is malleability. While ductility means that it can be drawn into what? Into wire. You know, like some of you play with chewing gums, right? They bring or chewing gum or plasticine or something, okay? Or glue, you draw it like that, or rubber band. You can draw the rubber band. That's what we call ductility. If it's a metal, you are drawing like that into thin wire. They will say that that metal has a property called what? Ductility. Is ductile, okay? So the properties of metal being ductile and being malleable is as a result of what? Of the strong metallic bond. It means that the layer of metals can slide, the upper layer can slide over what? The lower layer without breaking the metallic bond. That is the sequence of explanation. Why are metals malleable and ductile? The upper layer can slide over what? Over the lower layer without breaking the wall, without breaking the metallic bond. That explains why metals are malleable and what? Ductile. So the layer keeps sliding over one another without breaking the bond. And of course, you can one of the best way I explain how these layers slide over one another is many of you have gone for skating, right? your skateboard. Your skateboard has a tire, okay? And so you can roll on the floor, right? See this tire as a sea of delocalized electron. And you see this what? This skateboard itself as what? As a positive metal core. That explains why the upper layer can slide over the wall, the lower layer easily, but without breaking the wall, without breaking the metallic bond. Are we making progress, guys?
Yes, sir.
Okay, so now let's explain thermal conductivity. Then when I explain I give somebody opportunity to explain electrical conductivity. So thermal conductivity. So who is explaining thermal conductivity? Why do metals conduct heat energy?
They conduct electricity because they have free electrons, available like free electrons around them, and they carry charges.
Fantastic. So we call the free electron what? Delocalized what? Electrons, right? Or you call it mobile what? Mobile electrons. Please don't call it mobile ions. Oh. It is called mobile electron. Don't ever make that mistake again. Mobile electrons, or you call it what? Delocalized. Okay. So when the metal is connected to the source of electricity, positive and negative. Of course, you know electricity is positive and what? Negative, right? Positive and negative. When you connect the metal, all the electrons, okay, will be repelled from the negative side and they will move towards the what? Positive side, right? Of course, you know, like charges what? Repel, or like charges attract. The electrons will move towards the positive side, while the electrons will be repelled from the negative side. That movement of electron is what we call electricity. Electrons moving in a city, right? Electricity. That movement of electron, because the electrons are mobile, they are able to shift. They are going to align in one direction when the metal is connected to the source of electricity. So all the electrons will drift towards the what? The positive pole. That drifting, okay, carries what? Carries charge, because when electrons move, they are going to carry charge. The carriage of charge, or the movement of charge, is what we call electricity, right? Okay, so that explains that. What about thermal conductivity? Why are metals able to conduct heat energy? Anybody? Why do metals conduct heat? Yes. Just relate that to the fact that metals are closely packed. You know, heat is conducted by three ways: radiation, conduction, and work conversion. In this case now, they are talking about conductivity, right? So it means that for something to be able to conduct, they must be in close contact. Because metals are closely packed, that close packing ensures that the metal particles are in touch. So when one end that is heated up vibrates, okay, so when you have a end, this end is have particles, okay? This place is, you have heat energy. You are heating up this place. When this particle vibrates, that vibration will touch the other one, will transfer the vibration to the other one, and they will keep transferring the vibration. Okay, as the energy is transferred, right, heat energy will also move from end A to what? To end B. Another reason is because electron itself that move from one end to another, electron is a particle. And because it is a particle, as it moves, it's delocalized. As the electron is moving from one end to another, it's going to be circulating the heat energy. So those are the two reasons why metals conduct electricity, because of the close packing, and because of because of electrons that move from one end to another. And because electron is a particle, it can conduct it can conduct heat energy. Okay, so far these are the general properties of metals that we have looked at: strong, malleable, ductile, sonorous, shiny when freshly cut, good conductor of heat and electricity, and they have high melting point and boiling point. They have high density. But I was able to differentiate between that and transition metals and group 1 metals for you. Right, let me show something from your syllabus. Okay, good. Look at this. Then I will go back to chemical properties of metal quickly. You can see it's as stated in your syllabus, transition metals. You say you should be able to describe transition metals as metals that are they have high melting point, they have high density, They form colored what? Compounds. And they act as what? Catalysts. Can you see these properties? These properties are unique to what? Transition metals. When they ask you to differentiate between transition metals and what? And group 1 or group 2 metals, these are the properties that you're going to mention. Group 1, transition metals have high density. Group 1 metals have low density. Transition metals have high melting and boiling point. Group 1 metals have what? Low melting and boiling point. Transition metals form colored compounds. Group 1 metals do not form colored compounds, right? Transition metals act as catalysts. Group 1 metals do not act as catalysts. Now, we treated Haber process and contact process. Can somebody mention two transition metals that acted as catalysts there in Haber process and contact process? What are those metals?
Iron and vanadium.
And vanadium. Yes. Can you see now? You are putting the big picture together. So another point, transition metals, they have what? They have variable oxidation what? Oxidation state. So that means that they have ions with varying what? Oxidation number. I'll give example here because it's a very, very important, very important. Okay. So let's look at this. Copper. And this is what? Copper. I need you guys to name it. Then I have this Fe2, okay, O3 and FeO. Yes. So this, who can name this oxide? This is copper what? Quickly. Copper, what is this?
So there's copper oxide, copper 2 oxide,
There's copper 2 oxide,
iron 3
iron
oxide,
3
and iron
oxide.
oxide.
Okay. So this is called copper. Now, the oxidation number that you guys learned, right? This is where we apply it. This is called copper 2 oxide. Okay. That's not like copper oxide, right? You must tell us, is it copper 1 or copper 2? Why this guy is what? Copper 1 what? Oxide. How did we get this? Remember your rules for naming, for calculating oxidation number. Rules for calculating oxidation number. What that rule tells us that the total oxidation number of elements in a compound is what? 0. Do you all agree with me? Are we on the same page?
Yes, sir.
Yes. So an oxygen is usually what? Minus what? -2, right? Except in peroxide, where it is what? Oh, okay. Oxygen is usually what? -2, right? So we don't know copper. So let's talk copper X plus what? -2 equals to 0. That means X is what? +2. Can you see why this is copper 2 oxide? So let's look at this copper 1 oxide. Everything must be equal to what? 0. Because the rule says the sum of the oxidation number of a compound equals to what? 0. So if oxygen is usually -2, I don't know what copper is. So let's say copper is X. I have 2 copper. So that is 2X, right? 2X plus -2 equals to what? 0. 2X minus 2 equals to 0. X is equal to what? 2/2, which is equal to what? +1. Can you see this is copper 1 oxide? The same thing applies to what? Iron. So this is what? Iron what? Anybody? Iron what is this?
Iron 3 oxide.
Iron 3 oxide. Iron 3 what? Oxide. You can just use the same formula. Why this guy is what? Iron what?
Iron 2 oxide.
Iron 2 oxide. It's very simple. Chemistry is simple. Just see the big picture, right? And what? And apply. So this is properties unique to transition metals. I want to ring this bell again. Number 1, transition metals have high density, high melting point and boiling point. They form colored what? Compounds. They act as catalysts. And they what? They have variable oxidation what? Oxidation state. I keep adding more. Number 6, they form more than one compound with the same element. And this is what exemplifies this. You can see. Can you see? Copper form more than one compound with the same element. Copper and oxygen. How many compounds did we get? 2. Can you see that? Unlike sodium. Sodium can form sodium oxide, and that's all. We don't say sodium 1 oxide, sodium 2 oxide. No, it's just sodium oxide. Can you see iron? Iron can form iron 2 and iron 3. And it's reacting with the same element. That is the meaning of variable oxidation state, or they form more than one compound with the same element. Do you guys get that? So let me now go back to chemical properties of what? Of metals. We have looked at physical properties. Now chemical what? properties of what? Of metals. In chemical properties of metals, there are three things you are required to focus on. Three things you are required to focus on. Number one, reaction with acid. Number two, reaction with cold water and what? Hot water. Then number three, reaction with what? Oxygen. So I'm going to simplify and take them one after the other, right? Your knowledge of ionic bond, yes, will help you here. Writing formula, equation. You need to be able to write word equation. You need to write word equation with what? State symbol, and write symbol word equation. Very, very important. So I take them sequentially. So let's take the first one. Number one. We are looking at the chemical properties of what? Of metals. Metals can react with acid. Okay. When we look at reactivity series, we look at metals that cannot react with acid and wine. But now, generally, we look at metals that can react with what? Acid, right? So metals can react with acid, and the general equation is metal plus what? Acid. What does it form, guy? What does it form? Salt plus what?
Hydrogen.
Plus hydrogen.
Plus hydrogen, right? Salt plus hydrogen, okay? So let's give a typical example. Somebody give me a metal. Give me a metal.
Potassium.
What? Potassium. So potassium plus acid. Give me an acid.
Hydrochloric acid.
You guys like hydrochloric acid like that. Okay. So this will give us what? Salt. Oh yeah, quickly. And then random. Potassium plus hydrogen. Yes, balancing it. We balance it this way, right? If you don't know how to balance this way, you learn how to balance from here. All the topics will enter into one another. So you can see we have balanced the equation, right? This is called what? Symbol equation. But I believe that everybody in this class should be able to write word equation. That's like year 8 word equation. Potassium plus hydrochloric acid, potassium chloride plus what? Plus hydrogen. We have gone beyond that level at this level. Okay. So then another thing you need to be able to do is what? State symbol. Potassium is solid. Hydrochloric acid is what? Aqueous, right? Potassium chloride form. Is it aqueous or solid or what?
Aqueous.
It's aqueous.
Good. Why is it aqueous? Anybody?
All chlorides are soluble.
Okay, because it's a what? It's yes. So you remember your table of solubility, right? All sort of potassium are soluble. Can you see that? All sort of potassium, sodium, ammonium, soluble, right? But chlorides are what? Soluble. But not all chlorides are soluble. Most chlorides are soluble, except we have exception. Lead chloride is not soluble. Okay. Mercury chloride is not soluble. Okay. Silver chloride is not soluble. Okay. So do you understand that? But most chlorides are soluble. So your sure bet here is that group 1 metals and group 2 metals, they are usually form soluble compounds, especially group 1. Do you get that? So that's potassium. Salt of potassium are what? Soluble, right? So you can see metal plus acid forms what? Salt and what? And hydrogen, right? So this is the reaction of metals plus what? Acid. We'll look at the exception later, okay? And we'll talk about displacement reaction and all that, but I don't want to jump out too many things at the same time. Now, cold water and what? And steam, right? Now, what metals can also react with water, okay? Metal can react with water. Now, if it is cold, right, it's going to form what? Metal what? Hydroxide and what? Hydrogen. Okay, metal, when it react with what? Water, form metal hydroxide and what? Hydrogen. Let's look at the typical example. Calcium. Calcium plus water. Okay, it's going to form what? Calcium what? Hydroxide plus what? Hydrogen. Now, I wrote this hydroxide this way. Can somebody tell me whether it is correct or wrong? And if it is wrong, what's the correct answer? What's the correct formula?
So it's wrong.
Okay. What's the correct formula?
CaOH2.
O2, right? Okay. Why is it going to be 2? Because of those
because calcium's valency.
Go ahead. Yes. Okay.
Calcium is 2 plus. And
Exactly. We'll switch, right?
Yeah.
Are you guys seeing my slide?
Yeah, we're saying so.
Oh, okay, good. Good. Okay, so you switch, right? You switch this, right? That's why we get in case somebody has forgotten. That's why I asked that question. So we can see this calcium word, hydroxide and word, and hydrogen. But some metals cannot react with cold water. In fact, their reaction with cold water is so slow, right? So we then say, okay, for this metal that can react with cold water, since increase in temperature, increase the rate of reaction, let's see if we can react this metal with steam. But before we go ahead to look at that, can we put state symbol here? This guy is solid. This guy is what? Liquid, right? This is what? Aqueous. Why this is what? Gas, right? So you must know that, right? So group 1 metals, okay, they form soluble what? Hydroxide. In fact, if you look at the reactivity series, potassium, calcium, and sodium, they form what? Soluble what? Hydroxide. From the reactivity series downward, other ones will form what? Insoluble what? Insoluble oxide. Insoluble oxide. And that starts from magnesium. So magnesium is the least metal among the reactive metals that can react, that can try to react with what? With cold water. So let me do that. Magnesium plus what? Plus what? Cold water, liquid, is going to give me what? Magnesium what? Hydroxide, right? Aqueous plus what? Hydrogen, right? I'm not sure my equation is balanced, so I'll balance the equation now, right? Okay, so, but magnesium reacts so slowly with cold water. We then react with the steam. So you can see this equation. Please, everybody look at this. This is gas. This is solid. Can you see gas, gas, gas? It means that it is steam, right? That's what we call hot water, steam, right? It is steam. So when a metal reacts with steam, it doesn't form hydroxide. What does it form? It forms metal oxide. So I'm going to be forming MgO, which is solid, plus what? Plus hydrogen. Can you see that? So it forms what? Insoluble what? Insoluble oxide, right? So every other one, iron and blah, blah, they form insoluble what? Oxide, right? So can you see that? That's the difference in the reaction between what? Metal and water, and metal and what? And steam. Okay? So the third reaction we are looking at is what? Metal and what? And oxygen. Okay, metal and oxygen. And this should be simple. Metal plus oxygen form what? Metal what? Metal oxide, right? So I need each of you to do example. Do example in your book. Just choose a random metal and what? Oxygen, and form the formula. I will call you randomly to tell me what you wrote down. Quickly, quickly, quickly. You have 30 seconds. We have a lot to look at. I have 6 more minutes before this time's out. You can see how time flies. Yeah. Okay. I'm looking at those in attendance. Adebisi Balogun. Okay. Aderi Sola. Gabira. Okay. Shemilore. Welcome. Tony. Tony Small, how are you? Can I hear you, Tony? Is she there? Arif is not here. Okay, who is true? Who is true? Olivia, what did you have? What did you form? Tell me the metal oxide that you formed. Yes, Otito. Otito, go ahead.
Calcium oxide.
Calcium oxide. What's the formula?
The formula for calcium oxide is Ca plus can I draw on the board?
You mean the formula or the equation? Just say it because of time.
The equation. Okay, Ca plus O2 equals CaO2. CaO2.
CaO2.
CaO, sorry, CaO.
CaO, okay, CaO. So you can then try to balance the equation, right? Okay, Ikman, go ahead. Ikman, go ahead.
Sorry, sir, did you call me?
Yes, Olivia. Is that Olivia?
Oh, it's Tony.
Tony, go ahead. Yes.
Oh, I have sodium oxide.
Sodium oxide. Okay. So what's your equation? Say it quickly.
Na plus O2 to
Yes.
Na plus O2 to NaO.
NaO. Yes.
Yes.
Okay. Your formula. Can somebody tell us what's not too correct with this equation? Anyway,
I think I can tell you. I
yeah,
think I can tell you.
go ahead. Go ahead.
I think it's Na. Is it Na2O?
Fantastic. Na2O. Yeah. Na2O.
Yes.
Na2O, right? Then we can have balance equation, right? Good.
Yes, sir.
Na2O. Na2O. So we balance this is 4, right? So these are little things, skills that you need to go practice, because if you don't practice them, they will hinder your progress in the topic. You understand the topic, but balancing equation, writing formula can then spoil your work. So please, everybody should go and practice that. I hope I could have longer hours with you guys, but let's keep moving on. I have a whole lot to touch for you. Okay, so this is the reaction of what? The reaction of what? Metals. General chemical properties of what? Metals. Limited to this, and we have looked at the word, the 3 of them. Reaction with acid, reaction with cold water, reaction with steam, and what? Reaction with oxygen. Okay, good. Now, this just explained a few things that we have looked at there. Okay, then I've also explained transition what? Transition metals, right? Okay, I've talked about transition metals and looked into all this. Then maybe next 3 minutes I can talk about these uses of metals in next 3 minutes. I think everybody should be able to know that, right? You need to know, this is white hat. You need to know the uses of what? The uses of metals, right? Ranging from aluminium and what? Copper. I mean, those are the key metals that we know. But use of metals like gold, silver, they are used for what? For jewelries, okay, because they have lustrous property. They sparkle, they shine, and all that. Okay, but aluminium, very key. What do we use aluminium for? It's one of the metals that is used for making aircraft, and the reason is because it has low density, unlike transition metals that have what? High density, right? So aluminium used for making aircraft, it has low density. Okay, then aluminium is used for the manufacturing of overhead cable. When we say overhead cable, we are referring to those electrical high tension wire. Exactly, high tension wire, electrical cables, right? If they use a metal that is heavy, that electrical cable will be falling every now and then. So they need to use a metal that both has good electrical conductivity and is also what? It has low density. So they use aluminum for overhead cable. Another property is they use aluminum for making what? Food containers, like all those milk, can for Milo. Inside they use aluminum, and sometimes they use tin. Okay, aluminum, because even you have what we call aluminum foil for covering your cake, pop-off, donuts, small chops and all that. Aluminum foil. It looks like paper, but it's a metal. Okay, aluminum foil, because it's not corrosive. Imagine using iron. Okay, iron to do your pot. Nobody uses iron pot, right? It's a metal pot, but it's usually aluminum pot, because aluminum will not rust and it will not stain your food. So the last one is copper. Copper has high electrical what? Conductivity. And so most electrical wires are made up of what? Are made up of copper, because copper is malleable and is ductile, right? And it has high what? Electrical conductivity. Okay, so when we come back from the next interlude, I'm going to go straight to alloys, then we'll move into basically redox reaction. Okay, so I hope you have your cup of tea and popcorn there with you guys. Okay,
Yes,
so just get something beside you and be munching. Copper is cheaper compared to some other metal with low resistivity. Fantastic, Farida. Yes, copper is with low resistivity. Okay, yeah, low resistivity. So low resistivity means that it has high conductivity. That's what it means. Okay, she's